Hello. In this presentation, I'm going to talk about virtual machines, the Java virtual machine, and containers. I'm going to give an overview on these different types of abstractions and how they work together. So hopefully by the end of this presentation, we'll be able to answer the following questions. First one, how does a JVM or Scala app run locally? The second question, how do we run a JVM or Scala app in the cloud? Hint, it has something to do with virtual machines. Third question, what are containers? And then finally, we're going to be able to answer, should we run JVM in containers? So before we get started, just a bit of context for this presentation. I'm pretty new to Scala and JVM languages in general, and so I thought I made this presentation to help myself understand a little bit better how JVM runs remotely or in the cloud. So I did some Googling and I found out that with Scala, you start with a Scala source file, the file that you code, and that Scala file gets compiled into Java bytecode, so it's packaged as a jar. This jar is run by the JVM execution engine, which interprets the bytecode into machine code, which is then sent to the kernel, and the kernel runs it on the hardware, so your computer. When I think of Scala like this, it reminds me a lot of other languages that I've used before. A language like Python. So in Python, I put code in a file, but Python files, I don't compile. Instead, I just run them. But when I run a Python file, underneath the hood, it gets compiled into Python bytecode, and then this bytecode is interpreted into machine code by the Python execution engine. The machine code is sent to the kernel, and the kernel runs it on the hardware. So that's Python, but JavaScript is also the same thing. When I run my JavaScript source file, it gets automatically compiled to bytecode, and this bytecode is interpreted into machine code by Node, and that machine code is sent to the kernel. So it's interesting comparing these languages because even though Python and JavaScript are scripting languages, they're a lot like Scala when I frame it like this, and Scala is a compiled language. And even Node even has a JIT compiler, just like the JVM. So a lot of things in common between these three languages. So this is how you run Scala locally on your machine. The question is, how do you run Scala in the cloud? And in order to answer that, we're going to need a new box in this diagram. So let's reset a little bit. We have the hardware, which is my computer, the kernel, which is the OS, and we can run apps on my OS, so something like a JVM app. But there's a different type of app that's a little bit special, and that's called a hypervisor. A hypervisor, one example of a hypervisor that you might know is something called VirtualBox. So I have VirtualBox installed right here. And VirtualBox is basically a piece of software that lets me run another operating system on top of my computer's operating system. So here I have Ubuntu running, and in the window, you can see that this version of Ubuntu, it's like a fully working version of Ubuntu. It behaves just like a regular PC. I can install and run programs like Firefox and VS Code on it, and it kind of does all the things Ubuntu would do if it was installed directly on my laptop. One thing I do want to point out here is this instance of Ubuntu, it's sandboxed from the rest of my computer. So if I open up Activity Monitor or System Monitor inside Ubuntu, and I look at the list of processes, I want to point out that these processes are completely different than the processes I see on Activity Monitor inside OS X. So in that regard, the stuff happening in Ubuntu is very opaque to my host's operating system. So let's get back to the slide. So here we have hypervisor, which is like VirtualBox, And on top of the hypervisor, I can install an operating system with a kernel, and I can install and run stuff on that operating system. So VS Code, Firefox, or a JVM app. So that's the hypervisor, but this is all still running on my computer. How does a hypervisor help me run a JVM app in the cloud? So to answer that, we have to look at the hardware. So cloud providers like AWS, they provide hardware, of course, but they don't give you access to install OSs directly on the hardware. Instead, cloud providers, they provide a type 1 hypervisor. So something really similar to VirtualBox, but with two key differences. The first difference is the type 1 hypervisor that cloud providers provide, they're installed directly on the hardware, and that's for optimal performance. So it gets you better performance than something like VirtualBox. The second difference with the type 1 hypervisor is there's typically no GUI. So in order to create start, stop operating systems on this hypervisor, you need an external client to connect to it to send those commands. But aside from those two differences, type 1 hypervisors are pretty similar to VirtualBox. I can install an OS on my type 1 hypervisor, run it, install and run apps on that OS, and I can even have multiple OSs running on my type 1 hypervisor. So in this diagram, my operating systems are my virtual machines. And these virtual machines, that include the OS, the kernel, everything the OS depends on, and everything that runs on top of the OS. In that regard, the virtual machine is how I run a JVM app in the cloud. So in AWS terms, the virtual machines are like my EC2 instances, and this client all the way to my left, that's kind of like the AWS web console that I use to provision, start, stop EC2 instances. So we talked about virtual machines here, but if we look closely to the diagram, the word virtual machine, it appears in another part, the JVM. And once we notice this, we ask ourselves, is this a virtual machine too? And the answer is obviously no. It doesn't include an OS, doesn't include a kernel. In fact, the JVM, it's a lot more like a single process than an entire OS. And in that sense, the JVM resembles a container more than it resembles an actual virtual machine. So what's a container? So when most people hear the word container, they think Docker, but I think some people would be surprised that the first version of Docker was nothing more than a thin API that wrapped features that were native in Linux. So let's take a look at those features that it wrapped. So in Linux, you can run programs and they run as processes, just like any other operating system. But the cool thing about Linux is there's this feature called namespaces that allow you to give specific views of shared resources to your programs. So namespaces come in different types, but let's look at an example to get a better understanding. So one type of namespace is called a mount namespace. And if I were to create a mount namespace and attach it to this JVM app running, I could give this JVM app a unique view of the file system that could be different than how the file system actually looks like in the OS. So to explain this a little bit better, I even have a small demo. So if I go to terminal here, on the right side, if I type ls, and in my root folder, I can see a list of files and folders in root. On my left side, if I ran shell inside a Docker container and then did ls root, I get a different list of files and folders. And the difference is here, this is possible because of namespaces. So namespaces, that feature is able to give my shell inside this Docker container the ability to see the file system differently. So just a disclaimer, Docker currently, this version of Docker doesn't use namespaces under the hood, but the first version did. And this demo was more to just kind of show you, to help explain what namespaces are. So that's one type of namespace. Another type of namespace is the process namespace, the PID namespaces. And this is just like the mount namespace. Instead of giving a different view of the file system, the PID namespaces gives processes their own view of the other processes that are running alongside it. So kind of like the PS command. Actually, I'll show you a demo here. So I can do PS here. I have one list of processes, but if I do PS inside my container, I get a different list. So there's about 8 or 9 different namespaces, I think, but the third namespace that I want to show in this diagram is something called the C group namespace. So the C group namespace is a little special because it actually doesn't give your processes a view of anything. Instead, the C group namespace is used to group processes together for the C group feature in Linux. So C groups is the second feature that the Docker API version 1 wrapped in the beginning. And C groups, it's pretty simple to explain. It's just a mechanism that allows you to control and manage CPU and memory usage. So namespaces, C groups, both native Linux features, and pretty much all you need to create a container. So now when you think of Docker, at least the first iteration of Docker, when it first came out, Docker run was basically just calling LXC, which is Linux containers, the library, something that's also bundled in Linux. And Docker would use LXC to create and manage namespaces and C groups. So that's what a container is at a high level. So now we know what a container is, we know what a virtual machine is. How do they compare when we think about running a JVM app? So let's kind of reset the diagram here. We have basically 2 ways to run a JVM app. One way is using a virtual machine, and that's kind of like the EC2 instance. The second way is using a container, and we just saw that a container is just a process, one or more processes, wrapped in some namespaces and a C group. This container is usually managed by Docker, and Docker is installed on some operating system. Something I want to point out in this diagram that's very important is the kernel. So the thing I want to point out is containers can share kernels, but virtual machines have a dedicated kernel. This characteristic is key when we think about the differences of running a JVM app inside a virtual machine versus a container. The first difference that I want to point out is size. So virtual machines, since they include the kernel and the operating system, they tend to be a lot bigger than containers. Virtual machines tend to be gigabytes or tens of gigabytes, whereas containers, they're usually tens of megabytes or even hundreds of megabytes, so orders of magnitude smaller. And the reason why size is important is it affects things like data transfer costs and startup times. So whenever you deploy an app or whenever you scale out a cluster, something like size, it affects those things. The second difference that I want to point out between virtual machines and containers is this idea of boundaries. So when we look at running a JVM inside a container, it's clear what the service team is responsible for and what the infrastructure team is responsible for. Service teams are responsible for the container, infrastructure is responsible for everything underneath. With a virtual machine, those boundaries, they're not as clear. Since the deployable unit here is the entire virtual machine, including the OS, you would think that the service team is responsible for the OS, but that's typically not the case. Usually someone else is responsible for keeping the OS up to date with security patches and whatever, but the issue there is it's hard for that someone else to know what parts of the OS the service depends on, because those dependencies aren't always clear. So something like boundaries, it's important to recognize because it affects things like security and user experience. The third difference that I want to point out with virtual machines and containers is this idea of utilization. So say I had a JVM app like a.jar. If I wanted to run this in a virtual machine, typically the smallest virtual machine practically has 4 gigabytes of memory. So if I wanted to run 3 different apps, say bjar and cjar, I would need at least 12 gigabytes. I would need to buy virtual machines that make up 12 gigabytes of memory. The issue with utilization comes into play if each one of these services are very small. If each one of these services required only 100 megabytes of memory, then I would have bought too much because I have 12 gigabytes of memory and I would be only using 2%. With containers, I can kind of avoid this issue since containers are able to share the same OS and essentially the same virtual machine. So in this case, if I have a.jar running on a virtual machine that has 4 gigabytes of memory and a.jar only needed 100 megabytes, then to start up B and C, I can just start it up on the same machine. And in this case, I would have so much memory left over that I could even scale out C.jar as well. So C.jar has high availability. I have multiple instances running, but really I only have to pay for one virtual machine here because my virtual machine has enough resources to be shared between all the containers. So at a high level, when you compare running something inside a virtual machine versus running it inside a container, size, boundaries, and utilization are the things I think of. And if you were to stop watching this presentation here, you would get the sense that I kind of want that you would get the sense that I would prefer running a JVM app inside a container, but I don't think that's necessarily the case. JVM and Java and containers, they're a weird match for a couple of reasons, but I'm going to focus on the 2 big reasons why they're a weird match. So the first reason why Java and containers are a weird match is this idea of container awareness. So earlier in the presentation, I talked about how Docker uses C groups to limit resources like CPU and memory. Well, here, the JVM, it also has a mechanism to limit how much CPU and memory it can use. The limits that it sets is set by a process called ergonomics. So ergonomics automatically detects how much CPU and memory to allow this jar to use. The issue here is ergonomics and C groups, they often develop conflicting views of CPU and memory limits. And whenever there's a conflicting view, it results in your JVM app crashing or unexpected behavior. These conflicting views can be explained by a small history lesson. So if we look at the timeline of Docker and Java, we can see that in 2013, Docker debuts, and also in 2013, Java 7 is released, and Java 8, work for Java 8 begins. So it's not until Java 9 that Java gets a chance to start making container features. So fortunately in 2017, Java becomes container aware, but 2017 wasn't that long ago, and it seems to be the trend that Java still kind of lags behind the container technology landscape. So that's the first thing that makes Java and containers kind of a weird match. The second thing that I want to point out is the glibc and muscle libc standard C library. So why does C matter with Java? Well, it's because the JVM is written in C++, and the JVM depends on glibc. The issue now, though, is for containers, The most popular Linux distribution that people use for containers is something called Alpine. Alpine, by default, is bundled with muscle libc, not glibc. And that means when you try to run JVM on Alpine, it just doesn't work. Fortunately, again for us, there's two workarounds for this. First workaround, you can just include the glibc standard C library in your Alpine Docker file. So just install it, and JVM should work. The second workaround that you can consider is maybe just don't use Alpine. Use Debian or use one of the Google distrolist images instead as a base image for your container. So those are two quirks that makes Java and containers a weird match, but there's workarounds there. But to be honest, I haven't actually had much experience working with them, so I don't know how great these workarounds are, but they're out there. So let's get back to the final question, the point of this presentation. It's should we run JVM apps and containers? And I've thought about this for a couple of weeks, and after a lot of Googling and doing this presentation, I've come to three conclusions. The first conclusion was one of JVM's main feature is this idea of portability, that I can write my Java or Scala app once on my computer and run it anywhere on any other computer as long as the JVM is installed. But when Docker gets introduced to this equation, that benefit of portability that a JVM language provides, it's not really that big of a deal anymore. I can do the same thing with Docker. I can create a Docker image, and I don't have to use a Java or a JVM language. I can use anything I want. And this Docker image, if it runs on my computer, then I'm pretty sure it's going to run the same way on another computer with Docker installed. The counter, though, here is JVM languages, Scala and Java, their tooling is exceptional, and in my opinion, far better than Golang or Node. So even though you're using Docker, I think that choosing a JVM language can still be a really good choice because of the tooling and even the community there. The second conclusion I came to was more microservices mean more chances to improve utilization. So microservice architecture seems to be really popular these days, and the tendency with microservices is not that you just get more services, but you get more small services. And the more small services you have, there'll be more opportunities to bin pack them and to run them on the same virtual machine, so you can improve efficiency and have cost savings that way. The counter here, though, is just because you do microservices doesn't necessarily mean you'll have small services. You could have just a bunch of medium-sized services. And if that's the case, then the opportunity, the savings, the potential savings you might get from running them on the same virtual machine might not be that big. And when you have something like autoscaling groups, that a feature that's provided by AWS and Google Cloud, if you have autoscaling groups wrapping your virtual machines, then they already do a pretty good job at making sure your services are running efficiently. The third conclusion I came to was maybe containers would improve user experience because developers won't have to deal with the OS. They won't have to worry about vulnerabilities or security patches. Containers will let devs just focus on what's in the container, and then infrastructure can focus what's on the OS. The counter, though, to this is maybe if you had an organization or an architecture that shared the same OS, so if they had different services but they shared the same OS that those services ran on, then maybe that work to keep the OS up to date is really little or nothing, because that burden, it's not just placed on individual teams, it's kind of shared with all the teams. So maybe there's not that much work there. So back to the question, should we run JVM apps and containers? And in conclusion, I'm not sure. There's a lot of pros and cons with running JVM apps inside of containers, And the pros, sometimes it's questionable how big those pros are. And um, yeah, I guess it depends on you. I know that's a little anticlimactic, but I hope this presentation at least gives you some better insight on those different abstractions, the JVM, virtual machines, and containers. So whatever you decide to do and whatever uh, code you're working on, hopefully this helps you make a more informed decision, whatever that decision is, containers or VMs. Anyways, that's my presentation. Thanks for watching.